Welcome. I'm Miss April, and we are on Chapter 12 today. We will be multiplying polynomials. So, in the last chapter, we added and subtracted polynomials. In this chapter, we're going to talk about different ways that we can multiply. So, if I give you something like 2x to the second power, and that's a monomial, and I want to multiply that by another monomial, let's say 3x to the third power. Remember all of our exponential rules, things that you probably should have memorized, right? When we are multiplying the variables, we have different powers there. Essentially what we're doing is adding these together. So I can do the coefficients first. 2 times 3 is 6. But I have x to the power of 2 and x to the power of 3. So I'm thinking 2 plus 3 gives me x to the power of 5. Okay. So that's multiplying a monomial times another monomial. And it doesn't matter how many monomials we have, as long as we remember our rules. Okay. Now remember with these, there's an unwritten 1 there. So when we go to add them together, keep that in mind. 3 times 2 is 6. 6 times 2 is 12. Now I'm thinking, okay, here I go, thinking again. X, I have 1, plus the 2, plus the 1. So I have x to the 4th power. Easy enough. Let's move on. Oh, by the way, it was 12.1. If you'd like, we can go ahead and do, let's see. Let's do number 5 and 12.1 so that you do see an example from your book. We have, that's number 5. We have a negative 2x squared y to the third. We're going to multiply that by negative 5 xy to the third, and again by negative xy. Okay, dealing with the coefficients first. Remember that there is a 1 here that we don't write. I have a negative 2, and let me just write my thought process. Negative 2 times 5, negative 5 times a negative 1. All right, we're multiplying. So we have 3 negatives. We know our answer will be negative. 2 times 5 is 10. 5 times 1. I'm sorry. 2 times 5 is 10. 10 times 1 is just 10. So then we have the next line of thought. X to the second power. Remember there's a 1 here that we don't write. A 1 here and a 1 here. So plus the 1 plus the 1. So what do I have? Gives me an x, 2, 3, 4 to the 4th power. Now let's look at our y's. What am I thinking? I have a 3 plus a 3 plus a 1. 3, 6, and 7. So I have y to the 7th power. When I go and I put it all together, I have a negative 10, x to the 4th, and y to the 7th. Okay, let's go to 12.2. In 12.1, we multiplied monomials by other monomials. So what happens when we have a polynomial? We're multiplying it by a monomial. Then we have to use the distribution property. For example, I might have 3x times x plus 5. There's my monomial there and a binomial there. I need to use distribution. So 3x times x gives me a 3x squared. So I did this. Now I need to do 3x times 5. 3 times 5 is 15. And there's my x. And that's about all I can do. Alrighty. What if I have something a little more complicated? And let's go to the exercises. And I want to look at number 9. So I have a negative 5x to the third, y to the second, 2x to the second, minus 6x, y to the second, plus 3. All right, so we need to distribute this first monomial to each term in this trinomial. Right, so I'm going to write the thought process, and you don't have to write this every time, but you do have to think it. So we'll do this times the first term. So I'm thinking negative 5 times the 2, thinking that first. And then I'm thinking x to the third plus the 2, because there's a x to the second power there. And then I just have the y to the second power. So this simplifies to negative 5 times 2 gives me a negative 10. 3 plus 2 is 5, so I have x to the 5th power. And just bring over my y squared. Okay. Now I'm going to do this monomial times this term in the trinomial. So I have a negative 5 times a negative 6. I have x to the third, and remember there's a 1 there. I'm adding the 1. Y to the second plus the 2. Putting all that together, a negative times a negative, 5 times 6, that gives me a positive 30. An x to the 3 plus 1, 4th power, and then a y to the 2 plus 2, 4th power. Now I distribute this to the third term. I'm thinking negative 5 times 3. Everything else stays the same because the 3 is a constant. There are no variables. So what do we have? Negative times a positive. Negative 5 times 3 is a negative 15. And I just go ahead and write these down. Now I put these in order. Negative 10, x to the 5th, y to the second, plus, that was positive, minus, that was negative. Okay, and that would be your answer. And you don't have to write it in every step like I did. You could just simply write it down as you go. I showed you my entire thinking process so that it would be abundantly clear every step that I took there. Let's move on to 12.3. Multiply. What happens when we multiply two binomials? If we have there are essentially a couple different methods that you can use for this. And let's examine both of them. The first one is to be sort of systematic, right? Let me rewrite this here. Where we are taking the first value, this x, and we are going to write out that we're going to multiply it by the x and then the 3 to each term in the binomial. And this is similar to distributing, right? We'll do that first. So we're thinking, I'll write what we're thinking. We're thinking x times the x first, okay? And then we're thinking x times the 3. Then we take the second term, the 2, in the first binomial, and we do the same thing. First, 2 times the x, and 2 times the 3. Now, you didn't have to write it out exactly like I did there, but if it helps you to think of it, you can do it that way. I have x squared. I have 3x, it's positive. I have a positive 2x. 2 times 3, that's 6. Now we want to combine like terms. 3 plus 2 is 5. Plus the 6, and that's it. Now, let's do another one. Using this first method, just so you can see, I'm not going to show all the thinking steps like I did this last time. Okay. So, oops, sorry about that. Lost the pen. X times x is x squared. X times the 2, 2x. Now I do this 2 times x. 2 times 2 is 4. Now I just have my like terms. And there we have it. Now let's take a look at the same problems using a different method. Method 2, or also known as FOIL, right? Many of you are already familiar with FOIL. So if we do x plus 2 and x plus 3 again, we can show this. What we're thinking with FOIL is first, outer, inner, last. First, x times x, x squared. Outer, I want to take these outer numbers. 3 times x, that's a 3x. Inner, let's take these inner numbers. 2 times x. And the last numbers. So this 2 is the last, and that 3 is the last. Combine those. Okay. Essentially, if you take a look, you can see that we have the same thing here and here. Okay, in the middle we have the 3x and the 2x. As long as you are systematic and you have multiplied the right numbers together, don't duplicate anything, then either method is going to work for you. FOIL is probably the most popular because it's systematic, very systematic. You do the first, you do the outer, and then you do the inner. Did I say we do the last? First, outer, inner, last. Easy. All right, so then if we're looking at exercises on 12.3, oh, let's take a hard one. Let's do number 8. Yes, you're welcome. Okay, looks like this. All right, I've written this down. So, I'm going to FOIL it. First, inner. Oh, I've got a negative there. Okay. Negative. And I will do it like this. I need to have an x times the square root 2. And really, so we can write it. I just don't want you to get confused if you've never seen this. You can write it like that and it means the same thing. Okay. Just don't use an x for times when we're doing algebra because that's really confusing. Okay, so we have this. Inner. That was the inner. So I must have done, I did first. This is the outer. I think I need more sleep. All right, so this is a positive. Okay, we have a positive now, and it's the same value. We have an x square root 2. Okay, then we have the last, because I already did the inner. So this is the last here. We have a negative. How do I want to write this? I'll do it like this. Okay, now I do want to show you, what does this mean? This means the same thing as this. Okay, and I want you to remember what happens, and we went over this in previous chapters, our rules when you are taking something that is squared already. We usually don't write the 2, but I want to show you. And we're taking that entire value and raising it to the second power. They negate each other. They cancel each other out, freeing up that 2, so that 2 is now free. Okay, so the square root and being raised to the second power, they're inverse operations. They undo each other, just leaves that 2 out there. And look what we have here. We have a minus this and a plus this. So they're gone, right? They cancel each other out. All we're left with is an x squared. And let's make sure we get the correct value here. This is a minus, okay? So we want to bring that down here. The sign is important. Okay, that's it. That was a fun one. Okay. Let's go to 12.4. 12.4. Now we're looking at something where we're multiplying 2 polynomials. And I'm going to go straight to an exercise to show you. Let's do number 7. A minus b times a squared plus an ab plus a b squared. Okay, for this one, we need to be careful and we need to be systematic. We're going to basically take this a and distribute it first to every term. Staying organized with this is going to be what's important. So, a times a squared. Remember there's a 1 there that we don't write. So we have a to the third. a times ab gives us a positive. A squared, right, because a1 plus the other one that's here and not written, a squared. And then we're just going to put the b there. Okay. Now, the a times the b squared, positive. And we have a, and then the b squared. Remember, when you have two variables side by side, the implied operation between them is multiplication. So when I write a b squared, what I'm saying is a times b squared. And we don't know what those values are, right? That's why it's a variable. It's an unknown. Okay, now we're going to take this b. We're going to do the same thing when we first distribute it here. And it's negative. Don't forget that. A negative times the positive a squared. So we kind of want to put them in ABC order. So I will put the a squared first, and then the b. So now negative b times ab. A negative again. Remember your proper sign. So I will put the a and then the b squared. Negative b times b squared. A negative b to the third. Okay. Now, to go through and combine like terms. We have a to the third. That's unique. I'll go ahead and write that down here. Then we have an a squared b. I have an a squared b here. Huh. Well, I have a plus an a squared b and a minus an a squared b. So they wind up canceling each other out. Okay. I have a positive ab squared, and I have a negative ab squared. That's what they do. They cancel each other out. Now I have this b here, this b to the third power, and it's a negative. That's the answer. Fun, fun. All right, let's move on. 12.5 deals with special products. What do we mean by that? Well, there are perfect squares. Perfect squares. That's not what we mean. So with perfect squares, I want you to think about what would yield a value. Let's say when we think about perfect squares and numbers, we think 25, right? Why? Because we know that 5 times 5 gives us a 25. It's a perfect square. There are no fractional parts of what we have to multiply together to get to 5. Or we could think of it as if we took the square root of it, we know it would be 5, right? So, other perfect squares, hopefully you've memorized them. 1, 4, 9, 16, 25, 36, and they just keep going, right? Those are perfect squares in constant values, right? Numbers, things that aren't going to change. They're not variables. So if it's a perfect square binomial, we might think of something like this. It would break down into, forgot my y. There we go. Right? Just like we had here, the 5 times the 5, it's the same thing times the same thing. And we could rewrite it like this, that's a perfect square. And it doesn't have to be addition, right? If I am working on something like this, I can rewrite it like this. It's a perfect square. Now, what that looks like in trinomial form, if we were to actually FOIL it through. Okay, let's move over here. So this one, if I FOIL the x plus y and the x plus y, I get x squared plus 2xy plus the y squared. Notice the x squared and the y squared on the ends, and you have the 2 and the xy in the middle. Being able to recognize this trinomial as part of a perfect square becomes very helpful to later algebra. So if we were to FOIL this one, then what's going to be the difference? We will have the x squared minus the 2xy plus the y squared. So when we have the binomial times the binomial and both of them are subtracted, then the first two terms are being subtracted and then you're adding, right? So again, this is a visual. When you see something in this form, think to yourself, perfect square. Another thing really important to recognize is a difference of squares. And the difference of squares, difference means subtract, right? Think you are subtracting perfect squares. So in variable terms, it looks like this. What is not a difference of squares is if I have something that looks like this. Not a difference, is it? We're adding. It's a sum. It's a sum of squares. The difference of squares is unique because when we pull it apart, or before we FOIL it, it has a unique look. We have x, it's always x plus the y, and then x minus the y. One is adding, one is subtracting, right? And it really doesn't matter which you put first. But let's see what happens when we add terms to that, and it has to be perfect square. I could say 25x squared minus 36x squared. That's a difference of squares, and it is because the coefficients will also square perfectly. So what do I know based on this? So I will have a 5x plus a 6. Whoops, I see what I did wrong there. That should be a y. Sorry about that. You're probably thinking, what? Okay. Plus the 6y. And then I'll have a 5x minus a 6y. If you don't believe me, you could FOIL that back through. Right? Perfect square. 5 times 5 is 25. 6 times 6 is 36. X squared is x squared. Y squared looks like y squared. So when you FOIL those back through, this is what you get. So recognizing that is important. There are also perfect cubes. Okay, so the perfect cubes, if you take the x, you can either add the y and you are cubing the whole thing, or you can subtract the y and you are cubing the whole thing. And visually they have specifics patterns in the way they look that you will learn to recognize as well. Y cubed. Okay, 3x squared y plus 3x y squared. And then you have the perfect cubes on the end, right? And that's all addition because this is addition. Now we have the subtraction, so we'll take the cubed and then we'll subtract. That first one has to be a subtract. The values themselves are the same. In the middle one, we're going to add. Then we subtract again. And that's just learning to recognize those as cubes, perfect cubes, when you see something that looks like either one of these, okay? We have a sum of cubes. All right, sum of cubes. So the difference between this and a sum of cubes would be that you have the cube that you're summing with another cube, right? So it's not the whole thing being cubed. All right, so what this looks like then when you factor it out, you have something where you have the, sorry, I'm having pen issues, okay, x plus y, and then you have the x squared minus xy plus the y squared, right? If you recognize that as a sum of cubes, that's helpful. The last one is the difference of cubes. Okay, so what do you think? Oops, cube. We have a cube. It's a funny cube. Hold on. Okay, difference. All right, and it's also very similar, only instead of adding there, we are subtracting. And then, oddly, we are taking the same numbers here, but we're adding and adding. Okay. Difference of cubes. Sum of cubes and difference of cubes. In exercise 12.5, you're asked to multiply as indicated. So if we take something like, let's grab number 9. They've given us 2m minus 1, and it's a 2. It is a difference, right? Subtraction means difference of squares. And if you remember, when I gave you the example for that, we had the x minus the y is 2, right? So yes, 1 is a square. We said 1, 4, 9, and we just kept going, right? So 1 is a perfect square. So we should know that we can rewrite this. We have it being squared, so we have 2m, right? And maybe you remember the pattern that this winds up being in. If you don't, FOIL it out. Okay, we have a 4m squared. And if you're foiling here, because if you don't recognize what it looks like, that's fine. First, outer. So you have negative 1. So you have a negative 2m when you multiply that out. Inner, again, a negative 2m. And last, negative 1 times a negative 1 gives us a positive 1. Combining like terms, these in the middle, that's the 1. Okay, well, this concludes chapter 12. I hope that's helpful, and I will see you for chapter 13.